Swayam Prabha. Digital India. Educated India.
So, welcome to today class of nonlinear vibration. Today class we are going to study regarding this chaos or chaotic responses in the system. So, already you have learned that we have 4 different type of responses in the system. So, they are fixed point response, periodic response, quasi periodic response and chaotic response. So, 4 different responses you have studied. So, first one is the fixed point response, second one periodic response, then quasi periodic response, then chaotic response. So, in case of fixed point response, so you have a fixed number fixed, and then in case of periodic response the response is repeated with a particular time interval, and in quasi periodic response particularly these are aperiodic response. So, where the frequencies ratio of the frequencies are in irrational number. So, for example, so you take y equal to 5 sin 2t plus 5 sin 2 root 2t. So, in this case the response will be quasi periodic, and the response, so the deterministic response, so all these responses are a deterministic response. That means you can determine, so what will be the amplitude of the response or what will be the frequency of the response. So, those things can be determined. That is why these are deterministic response. So, out of all these deterministic response, so which are not fixed periodic, not quasi periodic, are known as chaotic response. So, there is no standard definition of this chaotic response, but it is written in a negative way, that is the response, the deterministic response which are neither periodic, fixed point or quasi periodic are chaotic response. So, the characteristic of chaotic response is that, so it is very sensitive to initial condition. So, these are sensitive to initial conditions. So, if you change slightly the initial condition, so if the initial condition is changed slightly, then it will lead to another attractor. Initially you have got one chaotic attractor, so now slightly by changing this initial condition, so you can reach with another chaotic response. So, that is why they are also known as, or this effect is also known as butterfly effect. The sensitivity to initial condition which leads to different type of chaotic attractors are known as the butterfly effect. So, in chaotic responses particularly you will be seeing this butterfly effect. In actual case, in all higher dimensional system you can get chaotic response in the system. Last time when we have studied a base excited cantilever beam, we have studied a base excited cantilever beam whose equation can be written in this form, that is un double dot plus 2 epsilon zeta n un dot plus omega n square un. So, then we have a parametric forcing term, that is this f n m u m cos phi tau. Then we have this nonlinear terms also. So, geometric nonlinear term and this inertia nonlinear term. the second order differential equation, so containing so many nonlinear terms, and this parametric term actually will leads to chaotic responses. So, in addition to the fixed point, periodic and quasi periodic response, so last time we have seen several chaotic responses are there. So, in a general simple systems, for example, in the simple spring mass damper system also, when you are writing that equation as a doping equation by adding this nonlinearity. So, by changing the system parameters, you can see that chaotic responses also can be observed in that system. So, in this particular system what we have studied last time, that is a cantilever beam, base excited cantilever beam, and here the mass is put at arbitrary position. So, by adjusting this mass at arbitrary position, so we have seen, so we have found the second mode frequency, the ratio of the second mode frequency to first mode frequency equal to 3:1. We can also, by adjusting this thing, so we can have other different type of relations. So, that means omega 3 is to omega 2 is to omega 1 can be of 5 is to 3 is to 1. Similarly, we can get 9 is to 3 is to 1 also. So, 139 or 135. So, this way we can generate different type of resonance conditions, and here the base is excited. So, we have taken this base excited Z equal to Z0 sin omega t. So, depending on the value of this omega and Z0, that is amplitude and frequency of this base excitation. So, we can have different resonance conditions. So, depending on all these resonance conditions, so we can study or we can find so different type of chaotic responses. In chaotic response, so this chaotic response also can be observed in many fluid mechanics or fluid related systems, or in any mechanical systems, many other mechanical systems, biological systems, or electronically excited system, or electronic systems, electrical systems. So, in many systems, almost in all real life systems, so you can find this chaotic response, and this chaotic response, the application of chaotic response also can be, there are many applications of this chaotic response. Those who are interested, they can see the journals like this chaos, soliton and fractals, or this nonlinear dynamics, journal of sound and vibration, journal of vibration and control. So, in all those journals you can find the latest papers related to chaotic field. So, or you can see there are several systems, so where these chaotic responses can be found directly by using this Runge-Kutta method. So, you can find the response of the system at different value of this forcing, amplitude and frequency. So, as already told, so there will be several resonance conditions. So, this particular resonance condition has to be studied to find the response of the system, particularly when you are interested in a nonlinear system. So, that time, due to the presence of multiple solutions, so you must know, so what is the initial condition, so which is giving rise to what type of, or which is giving rise to what equilibrium condition or what fixed point response. So, knowing actually this fixed point response or unstable fixed point response, which may be the root of the other types of non-trivial responses, you can study the responses found in these particular systems. Here, when we are using this method of multiple scale, so you just see we have reduced this second order differential equation to 4. So, this is one, this is the second one, this is the third one, and this is the fourth one. So, 4 first order differential equation. So, these 4 first order differential equation can be solved numerically to find the responses of the system. So, already I explained that there will be multiple solutions, multiple fixed point response. In addition to that, there may be quasi periodic, periodic, or these chaotic responses. So, all these responses may coexist, and these due to this coexistence of different type of responses, they may interact also with each other, and due to that interaction sometimes some of the attractor will be disappearing or some of the attractor may appear in a bigger way. So, all those things will leads to this crisis in a system. So, we will see how the crisis can occur in the system, how this chaotic response can give rise to crisis when it come in the vicinity of an unstable periodic response. We have already plotted this, or we have seen this instability region. So, in this instability region, for example, so if we are taking a point here, so whatever may be, we have taken a point here. So, now by increasing the frequency, you can see whatever may be the frequency. So, up to this level, so there will be the system will be in trivial state, that means this cantilever beam will not vibrate. So, it will not vibrate or it will be in its trivial state, but if it enters into this zone, that unstable zone, so it starts vibrating in the transverse direction. We are moving the cantilever beam up and down. So, we have a mass attached mass here. So, it is moving up and down, but the beam is moving in a transverse direction. So, in a parametrically excited system, when we are giving a force in one direction, the displacement takes place in a perpendicular direction. So, here what we have observed, for certain value of this phi, that is the frequency and the amplitude of the base excitation, the response may be, or the system may be in trivial state or it may be non-trivial state. So, when we are using this cantilever beam as an energy harvester, so we can use this as an energy harvester. When it is used as an energy harvester, so we will be interested to run the system. So, in this zone, so in this unstable zone, so that we can get the non-trivial response, and due to the presence of non-trivial response, the voltage can be generated. So, if we are putting, for example, let us put some piezoelectric patch here. So, by putting some piezoelectric patch, so we can generate the harvester, or we can have, so for example, this cantilever beam. So, let us keep a magnet, fix a magnet here, and let we have some coil here. Due to the presence of this magnet, so there will be change in flux in this coil. So, when it is vibrating, so there is change in flux in this coil, and due to that thing, this EMF will be generated in these coils, and this EMF can be taken for harvesting the energy. Similarly, we may put, for example, so in this case we may put this blob body in this. So, let us put a blob body, and so when it is oscillating in this direction, and due to the presence of the blob body, due to, or let us take this simple cantilever beam, and this is the blob body and it is subjected to wind force. So, when it is subjected to wind force, so it will start oscillating, and this also give rise to, so if we will have the piezoelectric patch, so this will also give rise to this energy, so or this voltage. So, this way the same system can be used for many different purpose for harvesting the energy. Also, you can use different type of beam. So, instead of taking a simple elastic beam, so you can take this as a viscoelastic beam or the magnetoelastic beam. So, by taking magnetoelastic beam, so or viscoelastic beam, so you can achieve different purpose, and in all these cases you can see you can enter to a chaotic regime also. Also, you can take other different type of systems. For example, the simple system can be reduced in size and it can be used as a sensor, that is micro electromechanical system, MEM systems. So, it can be reduced to that of a MEM system. So, in which can be used for a sensor purpose, for making a sensor. So, there are several applications of this type of beam which you can study in great detail. Okay. Already we have plotted these response and bifurcations we have studied. So, you just see, so these are the points for Hopf bifurcation, so which will give rise to give rise to periodic response. Also we have the subcritical and supercritical pitch for bifurcation, particularly in case of subcritical bifurcation. So, if we reduce this frequency, as there is no stable zone, stable response near its vicinity, so the response, so there is a possibility that it may leads to a chaotic response. The system may jump up to a fixed attractor, a fixed point at the infinite, or it may have some chaotic attractor. So, near the periodic response, near the Hopf bifurcation, so we have periodic response. So, if there are some unstable periodic solution also, that may leads to, or that may gives rise to the chaotic response in that region. So, one should explore the possibilities of periodic, quasi-periodic and chaotic response near the unstable fixed point response. One can plot this response, that is amplitude versus this amplitude of the base excitation. So, here also similarly one can study all these bifurcation points. So, here we have seen, so near the Hopf bifurcation, so we have this period doubling, periodic, so we have a periodic response. Then this periodic response, by changing the system parameter, we have seen, or you can check that you can get the 2 periodic, and you can finally you can get large number of periodic, and it will leads to chaotic response. But how you will generate this thing? So, you have 4 reduced equation. So, these 4 reduced equation, so you use this RK4 method, so Runge-Kutta method. So, use RK4 or Runge-Kutta method. So, in MATLAB, so you have this ODE45 you can use. So, using this ODE45 function in MATLAB, so you can generate this periodic response. So, A1, A2, so all those things you can find. Then you can change the system parameter and check, so how these periodic response are periodic, then 2 periodic and 4 periodic, 8 periodic and 32 periodic, and finally it is becoming chaotic response. So, last class we have discussed regarding the Poincare section. Poincare section. If we know the period of this response, so if we can sample it with the time period, then for this single periodic, so we can get only one period, one point in this. For example, if I will take this A1 versus A1 dot, so there will be a single period. Similarly, so if it is 2 periodic, then there will be 2 points in the, so there will be 2 points near this. So, this is one point, then another point will be there. So, there will be 2 points. If it is 4 periodic, there will be 4 points, and also we have seen, so if the response is quasi periodic, then so it will be a closed loop. So, you will get a closed loop in the A1 versus A1 dot curve. So, this is displacement versus velocity curve, or you can plot A1 versus A2 plot also. So, there, so here you just see we have plotted A1 versus A2, that is the first 2 modes we have plotted. So, in the first 2 mode, here it is periodic, then this is 2 periodic, and finally it is chaotic. So, you can plot this phase portrait, so or the state space. So, when you are plotting A1 versus A2, so these are 2 different state of the system. So, that is why it is known as, so state space. So, you can plot the A1 in A1, A2 state space, these are state of the system. So, that is why it is known as state space. But when the response is chaotic, so if you find the Poincare section, so if you find the Poincare section, you can see that it will fill up the whole space. Initially you have a single point, then it becomes 2 points, then it becomes 4 points, and finally it filled up the space. So, if it is quasi periodic, then you will have a closed loop. When you are considering this chaotic response, then you must have to draw the Poincare section to check that it filled up the space. Similarly, you can draw or find the spectrum of the response. So, for a single periodic, so you have only one spike, so one frequency, it has one frequency. Similarly, for 2, so you will have 2 spike, and for multiple, so if you are plotting the spectrum, so this is your frequency. So, this frequency you can plot, and the spectrum here you can plot. For example, you can plot the displacement spectrum d star, let me put. So, in case of fixed point you have the spikes, but in case of this chaotic response, so you can have a broad band. So, the response may be so like this. So, the spectrum will be seen like this. So, this is omega versus your d star, that is your spectrum if you plot. So, if you plot the Poincare section, so this clearly shows this period doubling root to chaos. So, initially single period. So, in Poincare section you have a single point, now 2 point. So, here you have 2 points, here you have 4 points. So, that way you have seen. So, by changing this parameter nu, so we have seen in this case how the bifurcation is occurring. So, this point is a critical bifurcation point, and these and these points are critical bifurcation points. You can find the ratio. So, for example, this becomes 1 to 2. So, now this from 2 to 4, then for 4 to 8 you can see. So, this is 2, this is 2. So, after this thing, so you can have 8. So, then 16 you can use, there are certain theory or you can find. So, when this period doubling occur by using this Feigenbaum number. So, Feigenbaum is a universal number, that thing we will see after some time. So, sometimes you can get this crisis in this chaotic response. A crisis occur when a chaotic attractor comes into contact with unstable periodic solution. So, later before we have seen in the frequency response curve that in addition to this periodic response there exists the chaotic and quasi periodic response. Sometimes this chaotic response may come in contact with the unstable fixed point or unstable periodic response. So, you just see when we have plotted this A versus this omega. So, this A is nothing but the amplitude of the periodic response. So, actual response is u, which is equal to A cos phi t. Here this u, that is the response, is periodic, but we have plotted only this A versus omega in those curves. So, that is the amplitude of the response. Out of all these responses what you have plotted, so some of them may be periodic and some of them may be stable and some of them may be unstable. So, already you are familiar with the unstable or stable periodic response. So, by plotting the monodromy matrix, when you plot the monodromy matrix, so it must be within the unit circle. So, it must be within the unit circle. The eigenvalue of the monodromy matrix must be within this unit circle to have a stable solution. So, if you want to have a stable solution, so it must be unstable. So, if it is outside this thing, then it is unstable. So, here it is stable. So, if it is inside, this is lambda you are plotting. If it is within these eigenvalues, all the eigenvalues are inside this unit circle, then it is stable, and if it is outside, then it is unstable. So, these are the Foucault multipliers. When it is in +1, so then you can have a periodic solution. When it crosses the limits or the cycle by lambda equal to -1, then you can have 2 periodic solutions. So, all those bifurcations. So, that period doubling bifurcation. So, here when it leaves the unit circle through -1, so there will be period doubling, and that period doubling again may further double to have this period doubling root to chaos. If we have a unstable periodic response, we have a chaotic response and unstable periodic response, and the attractor passes through this unstable periodic response or touch this unstable periodic response, then suddenly it may disappear or it may explode. So, if it disappears suddenly, that attractor disappear and we are getting some resulting fixed point response or some periodic response, then that type of crisis is known as boundary crisis or exterior crisis. So, it is known as boundary crisis because later the response will be bounded to either a fixed point or a periodic response. So, this chaotic attractor will suddenly disappear. So, if it suddenly disappear, then we tells it as a boundary crisis or exterior crisis. And when it is coming in contact with an unstable periodic point and the attractor enlarges itself or explodes and the original attractor remain inside the newly formed attractor. So, then it is known as interior crisis. Sometimes there will be two attractor existing, and when it will come in contact with this unstable fixed periodic response, they merge and form a bigger attractor. So, this is known as attractor merging crisis. So, we have three different type of crisis. One is the boundary crisis or exterior crisis, when sudden disappearance of the attractor occurs. Then we can have the interior crisis, when suddenly it explodes and the original attractor remain inside the final attractor. So, and the third one is the attractor merging crisis. In 1983, Grebogi, Oat and York, so they have proposed these three different type of crises in physical systems. So, for the system what we have studied before, that is a cantilever beam subjected to base excitation. So, here we have observed, for example, so we have observed for nu equal to 0.5 and phi equal to 1.9, gamma equal to 8, we have this attractor. So, this is the attractor present at this point, and now, so when it comes in contact with another attractor, so slightly by changing this nu to 1, so you can see the same attractor comes inside. So, come in contact with a fixed point trivial response. So, this 0 is the fixed point trivial response. So, at that point the trivial response is unstable. So, this attractor comes in contact with the trivial unstable periodic response and it explodes to a bigger attractor. So, that is why, so this is known as interior crisis. So, you can come with a interior crisis. So, here attractor come in contact with unstable fixed point and explodes and gives rise to interior crisis. So, this is the original attractor and this is the attractor which explodes to form the interior crisis. So, similarly we can see some other different type of attractor merging crisis. Before, for example, at nu equal to gamma equal to 8 and nu equal to 0.01, phi equal to, so now we are changing phi. So, initial core phi equal to, that is the frequency of non-dimensional frequency of excitation equal to 1.81. So, when we slightly decrease that frequency, so you can see when we come to 1.79, so suddenly, so it come in contact with this unstable fixed point. So, these two attractor merge. So, these two attractor merge to form the chaotic response. So, here it is wandering actually for some times. So, it will be in the this left side and then suddenly it will go to right hand side and it will stay or graze for some times in this right hand side and then it will come back to the left side. So, this way these two attractor get merged and they form a bigger attractor. So, this chaotic initial chaotic attractor now becomes two chaotic attractor. So, these two merge to form a bigger attractor. So, this is known as attractor merging crisis. Similarly, there are some other routes to chaos also. So, initially we have a quasi periodic response. So, here the quasi periodic response is there for phi equal to 2.13, gamma equal to 8. So, we have a torus at nu equal to 8.5. So, now when we are reducing this damping, that is nu to 8.3. So, these are non-dimensional damping parameter. Nu is reduced to 8.3. So, from 8.5 to 8.3. So, you can see torus doubling root 2. So, this torus here doubled to have the root 2 chaos. So, torus doubling root 2 chaos one can observe here. Sometimes we can observe this torus breakdown to chaos, particularly this occur in case of a combination parametric resonance case, and here it is not shown. Coming back to the doping equation also. So, for example, we have seen this thing. So, in case of doping equation, by changing the system parameter, So, you can see this chaotic attractor. So, this chaotic attractor is nothing but, so it contain many harmonics in this response. So, by taking this, you just see here we have taken this delta alpha is nothing but this omega n square, delta is 2 epsilon zeta omega n. So, beta is the coefficient of cubic nonlinearity and r is the forcing, that is the amplitude of forcing, and omega is the frequency of forcing. In this case, you just see by changing the system parameter, so you are getting chaotic response. So, that is why you can tell that these nonlinear systems are generally, or nonlinear system generally does not obey the superposition rule. So, it will not obey the superposition rule. So, by changing slightly the system parameter, so you can have different type of response. So, it may be fixed point, may be periodic, quasi periodic or chaotic response. You cannot apply or you cannot predict. So, what will happen to the response at next moment when you are studying a nonlinear system. So, you have to properly study this nonlinear system and you can see how the displacement, velocity are evolving with time. So, here the time response is shown and you just see this curves, there is no similarity in this in the different periods. So, the shapes are very irregular and you can see how it wanders. So, from one orbit to another orbit. So, here also it may be attractor merging type of crisis will be there. So, when it is fixed point response, so you can have the homoclinic orbits. So, two homoclinic orbit, there will be heteroclinic orbit. So, this collapse of this homoclinic and heteroclinic orbit will leads to, so this type of chaotic response. So, this doping type of oscillator, so easily you can visualize. So, these are the equations where, or that of a spring mass system subjected to a forcing, where the spring you can take as a nonlinear spring. So, if you are taking a nonlinear spring with cubic nonlinearity, then it will be beta x cube only. These are the, this is a code written to find the responses using this OD45. So, initially, so you can have, for you just see, if you take this alpha equal to -1. So, here alpha is coefficient of x. So, if you have a equation x double dot minus, so this is alpha x. So, here if it is minus alpha x, you just see the auxiliary equation becomes d square minus alpha. So, the roots will be equal to, by putting it equal to 0, you can find the roots. So, the roots will be, d will be equal to, so d will be equal to plus minus root over alpha, d square equal to alpha. So, d will be equal to plus minus root over alpha. Here the solution, so this is real. So, from the solution you can see the system generally is, so one of the solution is must be greater than 0 and other solution must be less than 0. So, due to this thing, there the system will be generally unstable if you are taking a linear system with this. But when there is nonlinearity present in the system with the same doping type of equation with alpha, that is negative stiffness, taking the negative system, negative stiffness, the response is found to be bounded. So, you just see the response is bounded. So, here omega equal to 1.2, r you are changing from 0.2 to 0.28, here it is changing from a periodic response to a 2 periodic response. So, here it will be only single periodic and in this case it is 2 periodic. So, you can get 2 periodic response. So, then by changing this r, further by changing this r, you can see period doubling occurs and finally, you can have a chaotic response. So, this way you can, with a simple doping equation also you are getting this chaotic response. So, similarly from the quasi periodic response also, so you can get the chaotic response. So, when this breakdown or it doubled either torus doubling or torus breakdown, both will lead to chaotic response. Here we have taken a simple nonlinear spring with two, so let us put two forcing, so two harmonic forcing terms. So, one is cos 2t, one is cos 2 root 2t. So, in this case you just see by we can write down this 2 by 2 first order equation, and here the ratio of the frequency is root 2. So, you are going to get quasi periodic response. So, as it is nonlinear, so you can have multiple solutions also. So, you have to study which solutions you have to take for this multiple thing. So, already we know, so we have period doubling root 2 chaos, so we have quasi periodic root 2 chaos, and then we have this intermittency. So, we can particularly in case of fluid mechanics or fluid this turbulent flow, you can find this intermittency type of turbulence. So, then we have this crisis root 2, intermittency root 2 chaos, or this crisis root 2 chaos. Particularly if you study or take a delay differential equation, you can find chaos also. So, in addition to the physical systems what you have seen, so we can have some other system, for example, this Rosler equation. So, in this Rosler equation, this is a very simple equation. So, here this first order equations can be written x dot equal to minus y plus z, y dot equal to x plus a y, and then z dot equal to b plus x minus c into z. So, you just see by taking different parameter of c, taking parameter of c, one can get this initially this periodic, then it becomes 2 periodic. So, c equal to 8.5. So, we have period 4, then c equal to 8.7, period 8, period, so period 9, so period 12. So, different periods we can get. So, actual case this is a 3 dimensional system. So, x, y, z, but you can plot it using this 2 dimensional also, that is it is plotted for example x y, or it can be plot y z or x z. So, this is in 2 dimensional, it can be plotted in 2 dimensional or in 3 dimensional itself. So, we can define a number actually in this period doubling root 2 chaos. So, we can define a number, so which is known as Feigenbaum number. So, this Feigenbaum number can be defined by this alpha limit k tends to infinite alpha k minus alpha k minus 1 divided by alpha k plus 1 minus alpha k. So, this is the kth bifurcation. So, if we are taking, so for example, period doubling, so let period doubling start alpha. So, let us take k equal to 1. So, we can take k equal to 1. So, when it change from periodic 1 to periodic 2. So, when it is changing from periodic 1 to 2, so let us take it is alpha 1, alpha. So, we can take alpha 1, alpha 2, alpha 3. So, these 3 let us take. So, alpha 1 when it is changing from period 1 to 2. So, then when it is changing from period 2 to 3, so this is alpha 3, and period 3 to, so when it is changing from 1 to 2, that is alpha 1, and 2 to, so it will double. So, this becomes 2 to 4, then so it will becomes 4 to 8. So, it becomes 4 to 8, that is alpha 3. According to this Feigenbaum number, so delta will be equal to, so actually we have taken this first one, we have not taken k tends to infinite. Generally one should take k tends to infinite. So, delta can be written as, so by using this thing you can write this is alpha 2 minus alpha 1 by alpha 3 minus alpha 2. So, physically you can realize this Feigenbaum number like this. So, that is delta equal to alpha 2 minus alpha 1 by alpha 3 minus alpha 2. So, this number is a constant number. So, that value equal to 4.66292016. So, this number is same for all period doubling sequence associated with a smooth maps having a quadratic maximum. You can verify. So, I have shown you several period doubling route to chaos. So, for example, I have shown a parametrically excited system where you can find the period doubling, and also in this doping oscillator we have seen, and in this Rosler map also we have seen this period doubling route to chaos. So, in all these cases you can verify the Feigenbaum number. So, this is left as an assignment, so that you can verify this whether this Feigenbaum number is working there or not. So, you can generate a period doubling route to chaos by, or you can generate a chaotic response, for example, by simply writing your own code. So, for example, you just take u equal to, so this code is given here, you just take initialize. So, you have initially you have taken u equal to 0, initially you have taken u equal to 0, then you take u plus a0 cos II into omega t, where this II initially you have taken for first iteration it will be 1. So, for initially, so u equal to 0, then the next step becomes u equal to 0 plus a cos. So, here your IP equal to, so we have taken II equal to 2 to the power IP, that is it will be initially it will be 1. So, it will go on multiplying, II equal to 2 into IP, initially it is 1, then next time when it comes, so then this becomes 2 into 1. So, 2 into 1, that is 2, 2 to the power 1 equal to 2, then next time then IP becomes 2. So, this will be 2 to the power 2, that is 4. So, if you go on adding this thing, that is u equal to a cos, for example, a cos omega t plus a0 I have written. So, a0 cos 2 omega t, then you will have a0 cos 4 omega t, a0 cos 8 omega t. You go on adding, and for example, you go on adding and you plot this thing with respect to time. So, this will give rise to a curve. So, here we have plotted up to, so in this case we have plotted up to 7. So, we have taken this to 7. So, you can get a response like this. So, this response clearly shows the response is chaotic. You can plot this thing, you can plot the Poincare section. So, here you know what is the maximum omega you have taken. So, maximum omega, for example, you have taken 2 to the power. So, as IP you have taken 7. So, you have taken maximum, this is 2 to the power 7. So, 2 to the power 7. So, 2 into 7 times you can multiply these 2 and you can find 6, 1, 2, 3, 4, 5, 6 and 7. So, this is 16, 32, 64 and 128. So, you have taken 128. So, your by taking here we have taken omega, for example, omega we have started with 1. So, then finally, this is omega equal to, so omega 7 equal to 128 you have taken. So, the time period, so this will give to least time period. So, this will t will be equal to 2 pi by 128. So, by sampling the response with 2 pi by 128, so then you can plot the Poincare section. So, these Poincare sections will look like this. So, it fills up the whole space. So, depending on the time up to which you are taking, so you can verify or you can visualize that the Poincare section is filling up the whole space in the phase portrait. So, that is why the response is to be chaotic. So, in case of, for example, you just take only 1 or 2 terms. So, if you take only 2 terms, then you can see you have only 2 points. So, if you take 4, so then you have 4 points, and if you can take more than that thing, more than 16 or 32, then it will completely fill up the space and the response will be chaotic. And here you can check your displacement is bounded, velocity is bounded. That is why this chaotic response is a deterministic response. So, here the response is bounded. Also, you can characterize this chaotic response by using this Lyapunov exponent, and this Lyapunov exponent or characteristic exponent associated with a trajectory are a measure of the average rate of expansion and contraction of the trajectories surrounding it, any system containing at least one positive Lyapunov exponent is defined to be chaotic. For the chaotic response or the chaotic system, at least one of the Lyapunov exponent must be positive, and it can be shown that for a fixed point response. So, the existence of a fixed point response you can verify, or you can find the Lyapunov exponent and you can check that it is to be 0. So, the magnitude of the exponent reflecting the time scale on which the dynamics becomes unpredictable. So, what we can do? So, how to find this Lyapunov exponent? We can see what we can do. So, let us start with a initial point x 0. So, we have started with a initial point x 0 and we know with time. So, this will grow and this is the response of the system. So, now what you can do? So, you just start the same system with another points very close to it. So, this is x 0 plus delta you just take and then you find the solution. So, if you find the solution, so you just see initially this is the difference between this thing, initially this is the difference between this initial position and with time t. So, you have seen the difference grows. So, this is the difference. Now, the difference is this. So, you have seen the difference has grown. So, the difference has grown and so this is the next, this is the difference. So, here the difference is delta, but here the difference is very large. Any growing function can be written by using an exponential form also. So, by using some exponential form, so you can write the function and by taking that way, so we can determine this Lyapunov exponent. So, let us see, for example, consider the dynamic system. So, let us have a dynamic system x dot equal to f x mu. So, with time, so it will grow and the response can be written. So, you can find this x t equal to x 0 plus, or you can perturb this x. So, let initially it has a equilibrium solution. So, this equilibrium solution can be written as x 0. What is equilibrium solution? So, it satisfies this equation. So, that is at x dot equal to f x m. So, if x 0 is the equilibrium solution, then f x 0 m equal to 0. So, now you just perturb this x t. So, take x t equal to x 0 plus y t. So, the previous case I have taken this thing as delta. So, initially you have this is the equilibrium position. So, now you have taken perturb it and you have written this thing x 0 plus, you just write this is y t. So, because this delta will grow and you can write this as y t also. So, here by substituting this x t equal to x 0 plus y t. So, you can have this y dot. So, you can find. So, now you substitute it in this equation. So, this becomes x 0 dot plus y dot. So, it will be equal to f x 0 plus y m minus f x 0 m, as x 0 f x 0 m equal to 0. So, you know, so if x 0 is the equilibrium position, so f x 0 m, so it is equal to 0. So, by perturbing this thing, so you got this y dot equal to f x 0 plus y and m is the critical parameter what you are changing. So, this way you can find this y dot. So, y dot equal to, so by expanding that thing using this Taylor series, so you can write this y dot equal to f x 0 y m plus dx f x 0 m, so into y. So, this way you can write, but this part equal to, already you know this part equal to 0. So, this y dot becomes dx f x 0 m 0 and you can write this thing into y. So, this is equal to a y. So, this part you can write using a matrix. So, that is A. So, by using this A matrix, so this is nothing but similar to your this Jacobian matrix. So, this A y you can find. So, y dot can be written as y dot. So, what is y? Y is the deviation. So, how this deviation is growing? So, that is the, by studying that thing, so you can find the Lyapunov exponent. So, this is the A matrix. A matrix is nothing but del f1 by del x1, del f1 by del x2 and del f1 by del xn. So, this is for the first function. So, your f may contain n number of function. So, if it is n dimensional equation, so for example, in this Rosler equation, so you have 3 equations. In that case, your n will be equal to 3 and you have 3. So, your A matrix will be a 3:3 matrix. So, after finding this y dot equal to A y t, then taking different initial conditions. So, you can plot, so how much deviation it is having, what is the deviation. So, knowing that deviation, so you can find this Lyapunov exponent. For example, initially it is x0, now this becomes x0 plus delta, let you take. So, let this is the function. So, now at time t, so this has come x0 plus delta n. Here you have this with time. So, this becomes fn xn x0 fn x0. So, you can write this deviation delta n. So, this deviation delta n can be written as f n x0 plus delta minus fn delta. So, you can write this way, and this or this delta n you can write equal to delta 0 into e to the power n lambda x 0. So, this is delta n equal to delta 0. So, any growing function can be written by using this way, that is this delta n. So, finally, this deviation, let it is delta n. So, this delta n can be written, so f x 0 delta n minus f n x 0, that function. So, initially this is this, now it is growing to this form. So, this is your delta 0. This delta n can be written using this delta 0 by using this function, that is delta n will be equal to delta 0 e to the power n lambda. So, here this lambda is nothing but the Lyapunov exponent, which can be written as, you have seen this thing. So, you can write that lambda equal to 1 by n ln, so 1 by n ln, so delta n by delta 0. So, physically I hope you have understood that this is nothing but, so how it is either converging or diverging. So, that part we are checking. So, if it is converging, so this delta n will be less, and if delta n is more or it is growing, then if it is diverging, then delta n will be very high and delta n by delta 0 will be higher value, and if it is converging, then you can have a low value. Now, by taking this y t equal to phi t into y 0, so where this phi t is the fundamental matrix solution, so you can find this lambda I. So, that is limit t tends to infinity 1 by t. So, either you write in terms of this n. So, n step I have written this n is the n after nth iteration or after nth time. So, you are taking some time increment. So, for example, let you are taking time increment h. If you are starting with time t equal to 0, so after nth iteration it will be 0 plus n into h. So, that is why, so after nth iteration, so you can get what is the deviation. So, after knowing that deviation, so let the deviation is delta n, and initially it is delta 0, lambda equal to 1 by n ln delta n by delta 0. In this way you can find the Lyapunov exponent. In the next module, so we are going to study regarding the numerical methods used in this analysis of dynamical system. So, there we are going to study more on how to use or how to find this Lyapunov exponent. So, this you will find the code written for finding this Lyapunov exponent. So, here in this example I have given the time period is known to you, but generally in case of the experimentally obtained time series or obtain the time response, so the time period are not known. So, in that case, from the experimental data how you can determine this Lyapunov exponent also you can learn that time. So, in the next module you will learn all the numerical methods. So, here we have plotted this or you can take a Henon map to find the chaotic response. Rosler map already have shown. So, here this 3 dimensional plot is also plotted. Previously I have shown you this x versus y. This is the time response in case of a this time response for this Rosler map, Rosler equation. So, here you just see the time response, it is bounded, the response is bounded. So, it is within plus minus, this side it is minus 15, this side it is plus 20, but the response is not periodic or quasi periodic, and it is not a fixed point also, it is not going to a fixed point. That is why this response is chaotic. So, if you plot in xy, so this is the xy plot, and if you plot in xyz, so this is the plot in xyz direction. So, you can find the Lyapunov exponent in this case also. So, you can find the Lyapunov exponent, and we will see you can get the one, you can check that one of the Lyapunov exponent must be positive. So, you can see all these papers. So, for example, this is a very good papers. So, by H. Haken. So, at least one Lyapunov exponent vanishes if the trajectory of an attractor does not contain a fixed point. So, at least one of the Lyapunov exponent vanishes if the trajectory of an attractor does not contain a fixed point. Similarly, this is a very good paper. So, where this determining Lyapunov exponent from a time series. So, it is published in Physica D in 1985 by Wolf, Swift and Sweeney and Massano. So, generally it is known as Wolf's method for finding the Lyapunov exponent. Also, you can see this is another paper, a numerical approach to ergodic problems of dissipative dynamical systems. You can find it in this journal, that is Theoretical Physics. Then another one, that is strange attractor, chaotic behavior and information flow. So, these are very good paper in this field of chaotic response. So, now as you know how to generate this chaotic response, or you have seen in this physical system chaotic responses are there. So, you must know how to control this chaos. So, this controlling this chaos, determining the characteristic of the chaos are a subject of its own. We will study or we will give some example as an assignment to know how you can control this chaos. So, there are several methods to control the chaos. So, now what you have seen, so by using these exterior crisis or this boundary crisis, so if you can bring the attractor near to a fixed point response or near to one unstable periodic response, then you have seen that it disappear. So, that is one method you can use for controlling the chaos, that is known as this OGY method. Similarly, you can use some feedback control loop, you can use some feedback control loop to vary the system parameter and bring it to a domain where the response no longer is chaotic. So, it may be fixed point or periodic. So, the basic purpose is to change the system parameter in such way that, so it will be out of the chaotic domain. So, you have seen, so in between the chaotic region also you have a window of fixed point response or window where you can have fixed point periodic response. So, somehow by changing the system parameter using some adaptive control mechanism, so if you can shift or you can take that attractor to this that window where it is not periodic, then you will be able to control chaos. Sometimes these chaos are also necessary. In many places these chaotic responses or chaos is necessary. So, later we will see where these chaos are necessary when we will study the application of these nonlinear vibration systems. So, next class we are going to study the next module where we can study the numerical methods, and in this numerical methods particularly we will be interested to study how to find the roots of the characteristic equation, how to solve if you have a number of algebraic equations are there, how you can use this Runge-Kutta method, or there are some other methods, methods for solving these differential equations. So, all those methods we will study in next 3 classes by using different numerical methods. Thank you very much.